Okay, the next problem is problem 13. It wants us to find the derivative of this function right here. This obviously is just going to be 5, if you use the power rule. Do you know how to use the definition of derivative? This is probably the last time I'll use it just for sake of time in the video, but I'll quickly show you the work here for the definition of derivative. Let me write it down first. It's f of x plus 8, h minus f of x, all over h. The limit as h approaches infinity, so this would be 5 times x plus h minus 6, and then you'd also have minus the original function 5x minus 6 all over h. I want to take the limit of that, so it's just a little bit of algebra to simplify this. Let me just simplify it the next step for you. So you end up with this right here, and then obviously the 5x and the negative 5x cancel, the negative 6 and the 6 will cancel. You have 5h over h, the h's cancel. So obviously the limit as h approaches 0, that is just 5 as you evaluate the limit as well. So do you know how to use the definition of derivative as well as the power rule? So the domain of the original function is negative infinity to infinity, but they want us to use I, so that'll be negative I to I. And then actually the domain of the derivative is the same. You can stick whenever you want, it's just that you're only going to get out 5, obviously. It's just like, the line y equals 5. The domain is all real numbers, but the range is just 5. Okay, the next problem wants us to use the definition of derivative again. Let's just use the power rule. But know how to use the definition of derivative on a problem like this in case I were to give it to you on a test. But we'll do a shortcut here. This would be negative 9x squared minus 5. And then obviously if you take the second derivative, take the derivative of this, you get negative 18x using the power rule. You can do that in your calculator as well, but at a specific point anyway. But the power rule, you just multiply the exponent down and then lower the exponent. Okay, the next problem is pretty straightforward. We want to find the derivative. Let's just use the power rule here, which is 3x squared minus 90 for the derivative. And then the domain of the original function is all real numbers, and the domain of the derivative is also all real numbers. Okay, the next problem says a car position S is given by this table, so you have time and distance here. It says find the average velocity from 0 to 0.2 seconds. Well, we know that velocity is change in distance over change in time, so that's just slope. That's just the difference in the y's here, which is 0.35 minus 0, over the difference of the x's, which would be 0.2 minus 0. That gives you 1.75, and it does want the units here, so 1.75 feet per second. Now it's a little trickier for estimating the velocity at 0.2 because we're talking about instantaneous velocity now. So what we should do is we could use the average of these two, which is 1.75, plus the the average. Well, we want to take the average of that and the other interval right next to it, which would be from 0.2 to 0.4. So let's find that slope by doing 1.5 minus 0.35 over 0.2 minus 0, and that gives us 5.75, and then we can take the average of that, and we get 3.75. So if you look at a curve of this, the slope's changing. So if we're trying to estimate the slope at a point, what we could do is take the slope before it and the slope after it and just average it, and that should give us close to the slope of the tangent line, which is 3.75. Obviously, the other thing we could do is plug these in our calculator and get a function for this, a distance time function, and then just take the derivative of it. I didn't try that, but that would give us obviously then the instantaneous velocity at 0.2 if you just plugged in 0.2 to the derivative. Okay, the next problem wants us to find the derivative at the points 1, 2, 4, and 7. So at 1, the derivative is the slope, which is 0. At 2, the derivative is also the slope, which is 0. At 4, we have a slope of up 1 over 1. So the slope of 1 or a derivative of 1, and we have a slope of 0 at 7. Okay, the next problem, these might be a little hard to see here, but it says put the capital letter corresponding to the correct graph in the boxes below. So the sign we know is this one here, C. We know the sign starts off at 0 and increases. The natural log, you might remember, is A, which is the inverse of an exponential function. The exponential function then is D, inverse of the natural log. And then the derivative of the sine, this is a little tricky, but the derivative of the sine, you can tell the slope starts off at 1. you know, because the sign goes like this. So you can tell the slope starts off at a value of 1 right here, and then the slope goes to 0. Then the slope goes to -1. Then the slope goes back to 0. So actually what it is the cosine. The derivative of the sine is the cosine, which is e. And then the derivative of the natural log, if you take a look at the natural log function, you can see the slope starts off like almost at infinity, and the slope, you know, tapers off, as you can tell here. So that would be b. And then the exponential function looks like this. Well, the slope of that starts off at 0 and steadily increases until the slope goes to infinity, which is exactly what the natural log, or I'm sorry, the exponential function does itself. So the derivative of the exponential function is the exponential function, which is d. And that's not something you just necessarily have to know, but if given a graph, like, you can match these together by, you know, thinking about slope. If you stop and think about, you know, look at the sine function and what is the slope at each point and what's happening then to the slope. What would that graph look like? Well, that graph, the slope, it starts at 1, then it goes to 0, then the slope goes to -1, then the slope goes back to 0, so you can see it's actually the cosine function. So things like that. Okay, the next problem, I've drawn this piecewise function here just for the sake of drawing it. You don't have to do that, but it says this function is differentiable at x equals -1, but not at x equals 1. Can you see why? You don't have to answer that question, but I will for you. The reason why is because this is what the graph looks like, and at this point, it turns out that the slope of the green function at -1 is exactly, which is the line, is exactly equal to the slope of the parabola, the middle function, at x equals -1. Because if you take the derivative of both of them at -1 and plug that in, you get the same value, which is -12. So they both have a slope of -12 right there, which means it's continuous derivative, or they have the same slope there, so they have the same derivative. But at this point, obviously, there's no derivative. You can't take the derivative because there's an infinite number of tangent lines that you could draw there. There's no one tangent line, therefore there's no one slope, therefore there's no one derivative. So that's what they're talking about there, but that's not important. I'm not going to ask you that question. But let's find the derivative at x is less than -1. That'd be -12. And the derivative between -1 and 1, which would be 12x. And the derivative at x is greater than 1, which would be 6, using the power rule. Okay, the next question says, what values of x does this graph have a horizontal tangent? Well, this is a cubic function, and we know cubic functions look something like this. So we could have, you know, 2 horizontal tangent lines, right there and right there. That's where the slope would be 0. So let's go ahead and find the derivative of this, which would be 18x squared plus 108x. And this is the derivative. Let's find out where the derivative, or where the slope, is 0. So set this equal to 0 and solve. Let's factor out an x, and actually let's factor an 18 as well, and we'll get x squared plus 6 here. So we know that one of the places is at x equals 0. And I'm sorry, I took the derivative of this wrong, so we back up here. This is supposed to be 144 here as well. No, so we want to find out where this is 0. So then if we factor out an 18, we get this. And then if we factor it into this here, 2 linear factors, we get at -4 and -2, the slope of this function is going to be 0. And so those are our answers, -4 and -2. So I didn't draw this right, but those are what we need to put in. All right, next couple problems, let's do these numerical derivatives. You can do these in your calculator. This one's easy enough by hand because if you take the derivative of a constant, it's really 12x to the 0th. So when you multiply the exponent down using the power rule, you get 0. So the derivative of the function that they gave us is just 0. Therefore, you plug in any point, you're going to get 0. And like I said, in the calculator, you know, you can always double check these by doing alpha window, numerical derivative, which is 3, and derivative in terms of x of the function, which the function is 12 in this case. We want it at -3, and that's going to give us 0. Okay, the next problem then says, suppose that this is the function. We can actually do this by hand as well if we wanted to find the derivative of the original. If we write it like this, we can multiply down and get -78x to the -14th. there's the derivative, and then you can plug in, 3. Find the derivative at 3 if you wanted to. Negative 78 times 3 to the negative 14th, which gives you about negative 1.63 times 10 to the negative 5th, which, you'd have to carry the 5 over, so you have to make it negative 0.0000163 and enter it in like that. It's a small number, but you could also do this in your calculator by doing alpha window numerical derivative 3 in terms of x of the function, which I'll do 6 over x to the 13th, and we'll do that at 3, and that gives us the same answer. And then we could also just do it again, this time at negative 2, and that gives us negative 0.0048. Okay, the next question says you toss a rock up vertically at initial speed of 33 feet per second. The initial height is 6, so that'd be our equation for that. We have in a formula sheet. I think I use S for that in the formula sheet. I can't remember, but initial height equals negative 16t squared plus the initial speed in the y direction, which is 33 feet per second, times time, plus the initial height, which is in this case 6. So there's our distance time equation. Let's use D for that. And the first question says the rock will remain in the air for how long? Well, it's a parabola that goes like this. So if we just graph, and find out this point right here, the x value or the t value, that's how much time the rock's in the air for, this amount of time, because this is time. Sorry, this is time and this is distance. So we just want that time right there. That's not hard to do. Just look at the graph and do second calculate 0, and you should get 2.23 about. At least that's what I get. Okay. Next question then says it will reach its maximum height at. There's different ways to find this maximum height. It's a vertex of the parabola, so you could just do it in the calculator really quickly. But we could also take the derivative, because the velocity then equation in terms of time, if we take the derivative, which is the slope, you get negative 32t plus 33. And so where at the top, where the velocity is 0, that is the vertex, or that's the point we're looking for. So it would be subtract 33 divided by 32, you get 33 over 32 for the time. So that goes in here for me. And then I'd have to plug that time back in here in order to get the corresponding distance for that, which is the height they're looking for. If I do that, I get 23.02 about. Okay, this next problem is pretty easy. It gives us a distance time equation again. And this time it says find the velocity and acceleration of functions of time. Well, the velocity is the derivative of the distance, because velocity is the change in distance over change in time. So therefore the slope on a distance time graph, the slope is velocity because it's distance over time. So to find that, we just take the derivative. So the velocity would be 6t minus 2. And then the acceleration would be the derivative of that, which is just 6. So when they're asking for the acceleration, it's a constant at any time. So I can just enter 6 for those. Okay, the last problem then says coffee is poured into the mugs at a constant rate, constant volume per unit time. The graph shows the depth of the coffee in the mug as a function of time. So the answer is going to be B for me. And the reason why is because the shape of this mug right here, it's going to be able to fill up really quickly at the beginning because there's not as much volume, there's not as much space for the coffee to go. So it's going to fill up really quickly in the beginning because of the shape of the mug. And then in the middle, there's more volume, there's more cross-sectional area for the coffee to be. So it's going to go slower there, so the slope's going to go down in the middle. And then at the top, the slope's going to increase again because we're decreasing at the top of the coffee mug the amount of volume that's available. So it'd be B for me.